Hello and welcome to this open module, the Hofmann-Löffler-Freytag reaction. The Hofmann-Löffler reaction, also referred to as the Hofmann-Löffler-Freytag reaction or the HLF reaction, is an organic reaction in which a cyclic amine, a pyrrolidine, or in some cases a piperidine, is generated by the thermal or photochemical decomposition of N-halogenated amines in the presence of a strong acid, typically concentrated sulfuric acid or concentrated TFA. The HLF reaction proceeds via an intramolecular 1,5 hydrogen atom transfer to a nitrogen-centered radical and is an early example of a remote intramolecular free radical CH functionalization. In the late 1870s, A.W. Hofmann performed a series of experiments designed to determine the then unknown structure of piperidine. In the course of these studies, a series of N-haloamines and N-haloamides was synthesized, and Hofmann investigated the reaction of these species under acidic and basic conditions. He reported that the treatment of these molecules with hot sulfuric acid, followed by basic workup, furnished the corresponding tertiary amines. While this was an interesting result, the power of this reaction was unrecognized for nearly 25 years. In 1909, Löffler and Freytag extended the scope of this transformation and set the scene for it to become a general and straightforward method for the formation of pyrrolidines by demonstrating that the reaction was possible with simple secondary amines, showcased by the synthesis of nicotine. Mechanistic investigations of the HLF reaction. Although the HLF was initially discovered in the 1880s, it was not until the late 1950s that the mechanistic details of this reaction were understood. Two groups played a key role in these investigations. Warzenek and Thalen investigated the nature of this reaction, showing that it proceeded either when performed under irradiation with UV light in the presence of chlorine, or in the dark in the presence of the radical initiator hydrogen peroxide. Based on this evidence, they proposed that the reaction proceeds via a radical chain reaction pathway. Based on their investigations, they made further predictions about the nature of the reaction. They proposed that the first step is protonation of the amine by the acid, followed by homolytic cleavage promoted either by light or a suitable initiator to afford the aminium and chloride-free radicals. The aminium radical abstracts a sterically available hydrogen atom, producing an alkyl radical that in turn abstracts a chlorine atom from another N-chloroammonium ion, forming an alkyl chloride and a new aminium radical. Upon basic workup, nucleophilic cyclization occurs to form the tertiary amine. In the 1950s, the Corey group carried out a detailed and extensive mechanistic investigation of the HLF reaction, with a particular focus on the stereochemistry, the hydrogen isotope effect, initiation, catalysis, intermediates, and selectivity of hydrogen transfer. Using the deuterated amine, Corey et al. Were able to explore whether the replacement of hydrogen in the cyclization reaction proceeded with retention, inversion, or equilibrium of configuration. The product was found to be optically inactive, providing strong evidence that the intermediate species possessed an sp2 hybridized delta carbon. Using the deuterated amine allowed another important set of experiments to be carried out, enabling the determination of the hydrogen isotope effect. Analysis of the product mixture gave a value of 0.7 atoms of deuterium per molecule, corresponding to an isotope effect of Kh over Kd equal to 3.54. Verification of this value through comparison of the intensities of stretched absorptions in IR gave a value in good agreement, which was 3.42. These values suggest that the breaking of the CH bond proceeds to a considerable extent in the transition state. Building from the proposed mechanism, Corey et al. Were able to isolate the intermediate 4-chloride dibutylamine from the decomposition of dibutylchlorolamine in H2SO4. Treatment of the delta chloroamine with base furnished the cyclized products and a chloride ion. The investigators then turned to exploring the selectivity of the hydrogen transfer process. Systems were chosen with three perspectives in mind. A. The relative migration tendencies of primary, secondary, and tertiary CH bonds. B. The relative rates of 1,5 and 1,6 hydrogen rearrangements, and C, the facility of hydrogen rearrangements in cyclic systems of restricted geometry. In the first reaction, with competing primary and secondary CH bonds, only the product from the secondary CH insertion was observed, suggesting that the radical attack has a strong preference for the secondary over the primary CH bond. The next reaction looked at primary versus tertiary. While there was rapid disappearance of the starting material, none of the cyclized system was observed. The results suggested that there is a high selectivity for the tertiary CH bond, but the intermediate tertiary chloro compound was rapidly decomposed. A similar result was seen in reaction of secondary versus tertiary CH bonds, suggesting a strong preference for the tertiary CH bonds even over secondary CH bonds. In a competition experiment looking at the relative ease of the 1,5 and 1,6 transfer reactions, a 9-to-1 mixture of the 1,5 hydrogen transfer product was observed, showing good selectivity, though highlighting that appreciable amounts of the 6-membered ring can be formed. When cyclic and acyclic amines were subjected to the conditions, the cyclic systems were observed to be significantly slower, suggesting that the substrate's prevailing geometries were unfavourable for this reaction. Now we move on to the generally accepted mechanism of the HLF reaction based upon the findings in the 1950s. It is generally accepted that the first step of the HLF reaction conducted in acidic medium is the protonation of the N-halogenated amine. In the case of either thermal or chemical generation of the radical, the protonated ammonium salt undergoes homolytic cleavage of the NX bond to generate the N-centered radical. However, it has been argued that the UV-light catalyzed initiation involves the free form of the N-haloamine, followed by a rapid protonation of the newly generated neutral nitrogen radical. This was proposed by Corey et al. Studying the different absorption energy profiles of the different amine forms. Intramolecular 1,5 hydrogen abstraction is proposed to proceed via the outlined 6-membered transition state, explaining the observed preference for formation of the 5-membered heterocycles. The carbon-centered radical then abstracts halogen from a second molecule of the ammonium salt, propagating the radical chain. Upon treatment of the delta halogenated amine with base during the workup, nucleophilic cyclization affords the observed heterocycle. So this is a powerful reaction, but over the years people have explored ways to improve this, and this has resulted in a number of different modifications of the HLF reaction. One of the key flaws of the HLF reaction were the harsh acidic conditions required in the first step for the protonation of the N-haloamine. In many cases, this significantly restricted the substrate scope with respect to functional group tolerance and structure. A number of groups have explored solutions to this limitation. A key observation made by the Kimura and Ban group in the 1970s was that the incorporation of a nitrogen atom adjacent to the point of hydrogen abstraction significantly stabilized the resulting radical species, permitting this reaction to take place under mildly basic conditions. In their reports, they state the critical choice of triethylamine as the base in this reaction, which effectively neutralizes the hydrochloric acid generated through the cyclization process. The power of this approach was showcased in the synthesis of the natural product dihydrodeoxyepiallosemwine. Another approach to this was to put amides in the place of the amines. It was found that photolysis of the N-haloamide proceeds effectively under neutral conditions in generally very good yield. A powerful example of this was described by Baldwin et al., in which they rapidly constructed the core skeleton of the alkaloid galsemacine. Possibly the most important modification of the HLF reaction was first reported by Suarez et al. In 1980. Initially reporting a process using neutral conditions for the HLF reaction of N-nitroamides, the reaction was explored and optimized, expanding the substrate scope so that this transformation was effective for N-cyanamides, N-phosphoroamidates, and carbamates. All of these species react with hypervalent iodine reagents in the presence of molecular iodine, generating a nitrogen-centered radical via homolytic fragmentation of the iodoamide intermediate. This then proceeds via the established pathway to the heterocycles. There are a number of advantages to this strategy. This report from the Corey group built upon their mechanistic work to develop a rapid entry into the steroidal alkaloid derivative dihydroconosine. In the 1970s, the groups of Hoare and van der Woerd expanded on this chemistry in the preparation of a range of conosine steroidal alkaloid derivatives using the classical HLF reaction conditions with a strong acid. It was proposed that the ease and efficiency of this reaction was due to the nature of the steroidal substrate. Steroids are a privileged molecular scaffold, both in terms of therapeutic activity and development of new reactions. Many novel transformations have used steroids as an effective test substrate. In this case, the rigid backbone of the C and D rings brings the reactive groups into close proximity and an effective 6-membered ring transition state. The Suarez modification, capable of achieving the reaction under much milder conditions, has facilitated the application of this technology to a broad scope of substrates, including more functionalized molecules. In the top example, reported by Suarez in 1989, we have an example of the reaction of a series of medium-sized lactams, where the amidyl radical undergoes transannular hydrogen abstraction to form the bicyclic system. In 2003, Suarez et al. Also demonstrated that the chemistry was mild and tolerant enough to be effective with sugar derivatives, affecting a formal N-glycosylation reaction. As previously mentioned, steroids and steroidal derivatives have long been used as testing grounds for reaction development. Using the modified reaction conditions, Suarez et al. Were able to rapidly access a number of steroid and triterpene derivatives. Interestingly, the phosphoroamidate-initiated functionalizations were shown to consistently proceed with greater efficiency than those using the classical HLF methodology. In 2008, Baran et al. Reported a novel HLF variant. Employing a novel electron withdrawing group on the amide, an effective and general method for the synthesis of 1,3-diols was developed, starting from simple alcohol starting materials. This was further extended by Baran, where he demonstrated the power of this new variant as part of their concise total synthesis of pigmol using CH functionalization logic. So thank you for listening to this overview of the HLF reaction. We have a number of problems that are in the quiz, and there are some that you can also download and use to test your understanding and knowledge of this reaction, but explore some more of the open content with regard to radicals and how this has been extended to use in CH functionalization reactions.